Welcome to the first chapter of this class on partial differential equations, and we'll start with chapter 1 on ordinary differential equations. Let's start with giving the definition of an ODE. An ordinary differential equation, or ODE, is an equation that relates a function with its derivatives with respect to one variable. When there will be several variables, it will be called partial differential equations. The unknown is the function. What you're looking for is the function. And I believe that you've seen ordinary differential equations before. For instance, you've seen y prime equals my for m given a real number. And you're looking for all the possible functions y that will satisfy that equation y prime equals my. Now, ordinary differential equations are extremely useful when you model systems. And the reason is simple, because you often relate quantities with their variation, which happens to be the derivative. So you will see ODEs in pretty much every single field: mechanics, biology, chemistry, economics. You can basically name it, you will see ODEs there. And actually, right now, you're currently taking a class on modeling, and you will see that when you have continuous phenomenon, then you often have an ODE or a PDE when you have several variables that are playing a role here that will be useful to model your system. So we will actually explain and give a few examples on how we use ODEs, and we're going to call, when there is initial condition, we'll call that an initial value problem in the first section of this chapter. But that, again, is something extremely useful for modeling and for solving real-life problem, as the students like to put it. Now, there is a possible false belief that I would like to address now. The false belief is that solving an ODE is basically finding y of t equals something with respect to t. I mean, you've seen a lot of different ODEs in the past. Well, y prime equals my, which is obviously extremely simple to solve. Y second plus a y prime plus b equals f. Then you also have y prime plus p of t times y equals q of t of y. That's called the Bernoulli. And then you have the Riccati, and then the Clairaut, and then, you have a bunch of ODEs that sometimes, I mean, of course, you need to know them, because if you can solve this ODE by finding the closed form, in other words, y of t equals something, then of course you want to do it. However, please do not believe that this is what you do usually. In other words, usually you can't find the solution to the ODE in the sense of the closed form, the analytical solution, y of t equals something. It's not happening. Most of the time, you can't do it. So, and you know what? I mean, if you're the one giving the ODE to the students to solve, you can always change the ODE, right? For something you can solve. But, when you model the system, well, the ODE comes from the system. So it's not like you really have a choice of the ODE you're going to deal with. Or if you were to change the ODE just because of this, well, that would be really too bad. So here is going to be the modus operandi when you have an ODE. In general, it cannot be solved by finding a closed form. If it can, well, that's great. Great news. Let's do it this way. But most of the time, it can't. So when that happens, and for instance, you have y second equals negative sine y, which, by the way, just models the pendulum, then you're going to have to go a different route. And here's what you're going to do. First, you're going to basically, you want to figure out whether the solution exists. First, does it exist around the initial condition? In other words, in the neighborhood of the initial condition when you're basically going to fix y of t naught equals y naught, will you have a solution. And maybe actually when you have a second derivative, that neighborhood of y naught equals y of t naught equal y naught, maybe you're going to have to add something else, like for instance, y prime of t naught equals something as well. So the initial condition might depend on the ODE you have. Second question, if you're not exactly in this neighborhood, but you're further away, and even better, if you are if you have large values of t, what can you say? Do you have patterns that are periodicity? Do you have asymptotics? I mean, what's the situation? Can you actually say more than just what happens locally? Can you have a global view of what is going on for your ODE? 3, what happens if you have a small change on the initial condition? Instead of having y naught, in other words, when you have y of t naught equal y naught, instead of y naught, you have y naught plus a very small change. Does it change the solution significantly? And you see the problem. If the answer is yes, then from an engineering point of view, then that can lead to a lot of problems. And 4, well, can we actually compute numerically an approximation of the solution? Right? I mean, if you cannot find a closed form for y, well, the best you can hope for is to find a numerical approximation of the solution, and in which case you probably want to be able to guarantee to be as close as you want to the solution. Say, for instance, I don't know what the solution is, but I want to be able to find a numerical approximation that will be valid up to 10 raised to power negative 5, for instance. Can I actually do this? Can I find algorithms that will allow to compute numerically this solution? So that will be the MO for an ODE. And let's actually see the outline of this chapter and how we're going to go about each part of this first chapter on the ODEs. So we start with an introduction that you're currently watching. That will be the first video out of 12. There will be 12 videos altogether in this chapter. So the first section will be on initial value problems, and it will be composed of 2 videos. The first will be showing how we can use ODEs in modeling. And ODEs, that's ordinary differential equations, you will see soon enough that it's nice to also have an initial condition. And when you have an initial condition and an ordinary differential equation, then this is called an initial value problem. And in the second video of this section 1, in this section 1.2, in other words, chapter 1, 1.2, we will actually look at the Picard-Lendl of Cauchy-Lipschitz theorem. It could be a law firm, but no, it's a theorem that will actually tell us about the existence and uniqueness of the solutions to an initial value problem, in other words, an ODE with initial conditions. After this first section on the initial value problem and existence and uniqueness of this IVP, then we will discuss a specific case which is linear ordinary differential equations. And we'll have 3 videos. The first one will be on ODEs that are linear, but that are first order, there will be only one derivative, and that are scalar. That means that the dimension of the space where y takes its values is r, dimension 1. The r raised to power d, that means r. The second video will be with higher orders and still scalar. In other words, we'll have higher order linear ODEs, but still taking its values in r. And the third video will be about first order and vectorial, which means the function y takes its values in Rd. And as a matter of fact, we'll see, we'll actually spend a lot of time on the first video, how to deal with first order and scalar, a lot of time on the third video, first order and vectorial, and for the second video, we'll actually explain to you how you can basically not have to deal with higher order and scalar ODEs, and you can just transform them into a first order and vectorial ODE. So I don't want to spill the beans here. You'll just see how we do this in section 2.2. After this section on linear ODEs, we'll move on to some qualitative properties of the ODEs, and we will talk about the equilibrium of autonomous ODEs. So we'll define what is an autonomous ODE, and then we will actually introduce the theorem called the Lyapunov theorem and talk about linearization. And then section 3.2, we'll talk about chaos. After which we'll move on to section 4, that will be about numerical solutions, and there will be 4 videos in this section. The first one will be the Euler method, which will allow us to introduce that problem of finding numerical approximations to ODEs with an initial condition, also known as IVP. Then we will discuss discretization and k-step methods. After which we'll have a third video in section 4 about convergence. When we have numerical schemes, numerical methods, can we guarantee that what we compute, I mean the approximate solution, is somehow converging to the solution when what we'll call the step goes to 0? And we will finish that section 4 and this chapter 1 with a few methods, few numerical methods, and that after which you will be able to compute the numerical approximation of solutions thanks to the few methods that we will give you.